Okay, so previous lecture, we reviewed how to train the multi-class classification network, okay? Especially for digit classification, we use this Resnet architecture and have shown how we can train this network using Pytorch code, okay? And also we learned how we can use the GPU mode, okay? So we have to copy our data and also the model for the GPU drive to the GPU drive. Okay, so the grammar is very simple. We can specify this 2.2, okay, for model and the data. Okay, and you have to have proper GPUs already installed before using this grammar. Okay. And using the GPU, you can accelerate the training speed, okay? But the accuracy is same as before. Using CPU and GPU mode, the accuracy are same, but the training speed goes up, okay? And the next thing I want to explain you is the several CNN architectures, which are showing the state-of-the-art accuracy on this ImageNet dataset. Okay, maybe most of you are already familiar to this. So this graph I already show you before, maybe in introductory course class. I already show you this slide. Okay, and this in 2012 the Rscnn was appeared, and before this 2012, the state-of-the-art algorithm that performs best in ImageNet dataset was the shallow learning algorithms. Okay, we use the SVM to classify the hand-engineered features. Okay, but in 2012, the Rscnn appears and it records the 10% accuracy improvement. Okay, so this is kind of the first, working deep learning architectures. Okay, so after that, every computer vision applications are solved by the deep learning algorithms. Okay, and today I will show you what is this Rscnn, and what is Vision&Learning, and what is Google-led, and what is Resnet. Okay, so I think most of you are familiar with this, and I will accelerate the explanation for this part anyway. Okay, so this is the 4 features what Rscnn is having. Okay, actually, this Resnet was the architecture proposed in 1980s. Okay, before SVM. Before SVM, it was used, but in Resnet, there was some problem saying that it overfits to the data. Okay, so because the overall architecture size is large, to properly training this huge network, we need a large scale data. Okay, and also to prevent this overfitting, we have to involve some randomness. Okay. Maybe these 2 mechanisms are, the easy to think solution for preventing this overfitting. So, the philosophy in having large scale data is, if we can make our model overfit to the data, which is the large scale data, which we can see in the world. We can overfit our model to the images and their corresponding labels exist in the 그러니까 세상에 존재하는 모든 데이터에 오버핏을 시킨다는 얘기를 제가 계속 헤매고 있는데, so if we can overfit our model to the image data which exist in the world, okay, we can if we can overfit our model to the images which exist in the world, okay, then the model will see all the images in the world already during the training, okay, so it may perform well for testing data, okay. The testing, there would be no unseen testing data if we do that, right? So that is the ideal thing, okay? If we can overfit our model to all the images we are having in the world, then the model will work well, right? But that is not possible, okay? Impossible, right? We cannot show all the images in the world to the model during the training, okay? Because of the computational problem, and also we cannot capture all the images, okay, in the world, right? So because of that, we had to somehow constitute the large scale data, which is subset of all the images in the world, okay? But if we can increase the size of data, then the overfitting phenomenon decreases, okay? So we have to do some, maybe we already heard that the data augmentation scheme, right? A simple mechanism to augment your data, okay? And but the hurdle at this time in 1980s, there's not much storage, okay? And also there's no huge computational resources like GPU, okay? So having large-scale data set was limited at this time, okay? So the model, this Resnet, even though it has few layers, we cannot properly train this Resnet for real-world applications, okay? So people felt that this overfitting is really the problem in deep learning, and they did shallow learning before 2012, okay? And the other thing is, we can involve some randomness to the training algorithm to prevent the overfitting, okay? So we can add some regularization method involving this randomness to prevent the overfitting. So some schemes are newly proposed in Rscnn, okay? So this dropout is that kind of regularizer. So dropout during the training, if we use dropout, maybe I don't have, okay. Dropout, during the training, we randomly, this is some intermediate layers, we randomly turn off the filter corners, okay? So originally, let's say this is the ice layer, ice convolutional layer, and let's say ice layer, this is I+1 layer. And to connect these two layers, we may have some convolution operation. So for this channel, we need to have some dense connections to output intermediate convolution output for each channel of the next layer, okay? But we will randomly turn off some of the connections in between. So this is randomly done, okay? So during training, because of this randomness, the network could not be overfit to the training data. Okay. So but testing, we do not turn off these connections. Okay. So because of this randomness, during the training, we enforce the network not to overfit to the training data. Okay. So this dropout was the new scheme for that. And data augmentation, as I told you, so let's say this is the human, and this is, let's say, the ball, right? And even though we flip it, horizontally flip it, the content in this image is not changed, okay? So let's say this is human playing soccer, let's say. Even though we horizontally flip this image, their content is not changed and its label is still human playing soccer, okay? So, but we can supply twice of the data if we apply this horizontal flipping, right? And also we can change their color scales or add some noise and so on. So by incrementing the size of the data from the original image, we can make, let's say we have 10 times augment the data, I mean, make the new input image from the original image, then we can increase our data size by 10 times, okay? So anyway, this data augmentation scheme is for that, okay? So it is helpful for preventing the overfitting phenomena, okay? And previously, the sigmoid and tangent hyperbolic functions are used for the nonlinear layers, but there's some problem, okay? Because for for the sigmoid function, some gradients are not stable in this x point whose values are close to infinity. So it's not, their gradients are not stable. So, but the ReLU function, it looks like this. And for this, its gradient is always 0. And for this part, the gradient is always 1. So their gradient is better than previous nonlinear activation. So ReLU is first used in Rscnn, okay? And also, this network was first trained with multiple GPUs, okay? So even though it has more data via the data augmentation, and also it has more layers compared to Resnet, but using these multiple GPUs, this Rscnn was properly trained, okay? And using these three methods, this network recorded the state-of-the-art accuracy in ImageNet dataset. Okay, so because of this, it could generate this 10% accuracy gap. Okay. Okay, and this is the slide showing that how this Rscnn architecture is composed. Okay, so this is the Rscnn class, and the first part, it is the having the convolutional operations, and it is called as convolutional layers. And later part, it has linear layers, and it is called as fully connected layers, as before, similarly as before. Okay, so their architecture constitution is similar to Resnet architecture, but they are having more layers, and they have ReLU activations rather than sigmoid or tangent hyperbolic. And also they involve the dropout layers in the middle, okay? Okay, so this is the Rscnn. So, I mean, the convolutional layers in the forward, convolutional layers are first applied, and they average the middle features and flatten it and apply the fully connected layers. Okay. The overall architectures are quite similar to Resnet we learned, but having some more regularizer and some more newly introduced layers. Okay, and having more layers. That's the characteristic of the Rscnn. Okay, and after this, because of these features, the Rscnn made people to reuse this deep learning architecture for image classification tasks. Okay, and several groups are motivated to stack more layers compared to the Rscnn architecture. So Vision&Learning, it has maximum 19 layers. And also Google Resnet, it has 22 layers and performs better than Rscnn, okay? There's actually also the 10% gap between this Rscnn and VGG or the Google network, okay? Their motivation is if they stack more layers, they think they can increase the overall accuracy. Okay, so VGGNet tried to investigate the relationship between depth of the network and the overall accuracy. Okay, so compared to the Rscnn having like 8 layers, the VGG network the maximum depth of the VGG network is 19, but it is providing some intermediate models having less layers. Okay, it has the model whose name is VGG11 as well to VGG19. Okay, this figure after this VGG is denoting their depth. Okay. Okay. And when stacking more layers, they use the three by three corner rather than others. Okay, and they also use max pooling and fully connected layers after that. Similarly to the Rscnn, this is the fully connected layers after the convolutional layers. Okay, and they use mostly 3 by 3 filter corners when stacking these convolutional layers, okay? But in Rscnn, later part, it is using 3 by 3, but the first part, it has a large corner size, okay? This is 11 by 11, and this is 5 by 5, okay? But in VGG, they think this small corner size is effective, so they use these 3 by 3 corners. And this is the implementation for the VGG16 network. Okay. So they define several blocks in the constructor. Okay. And they are mostly having 3 by 3 filter. Okay. All of them are having this 3 by 3 as the filter. Okay. And the last layer is having the linear operation, and they apply these 5 blocks having 3 by 3 cornered convolutional layers and apply the F layer at the last. Okay, this is the VGG network. Okay, and the conclusion is if they stack more layers, the Rscnn is having 8 layers, but VGG network, it has 19, maximum 19 layers. And they draw some conclusion that if they stack more layers, the overall performance goes up. Okay. And this is the Google Resnet architecture made by Google. Okay. But Google Resnet is having some special basic blocks whose name is Inception module. Okay, this is actually the Inception module. Okay, so from the previous layers output, what this Inception layer is doing is they apply 4 parallel operations. The first is the 1-by-1 convolution. The second and the fourth is 3-by-3 max split. Okay, and then they concat all of the output. Okay, this is the Inception module. Okay, which is the basic block for the Google Resnet. Okay, and it has no fully connected layers at the last, but they say this Inception module is efficient and they can only constitute the overall architecture using this Inception module. Okay, and because of this, they could have 12 times less parameters than Rscnn, but they stack more layers. Okay, overall it has 22 layers, and they are using 9 Inception modules. Okay. And actually, this record better performance than the VGG network or the Rscnn. Okay. And this is the implementation for the Inception module, which is the basic block. Okay. What they do is they have 4 parallel operations: the 1-by-1 convolution, 3-by-3 convolution, 5-by-5 convolution, and the max 3-by-3 max split, which is these operations. They define it here, right? And then when X is inputted, they apply 4 parallel operations, and then they concatenate their output. Okay, this is the implementation for the Inception module. Okay, and then they stack multiple. They first define multiple layers. Okay, here, and you can see. So except for the first layer having convolution and max splitting sequentially, the other sub-modules are made of this Inception module. And at the last, it applies some dropout. And at the last, it applied the FC layer to map this intermediate feature to the 1000 dimensional class probability. Okay, so in here you can see how the forward function is defined. They apply from the image, they apply 5 layers they defined based on the Inception module and reshape it and apply this FC layer at the last. Okay, this is the Google Resnet. Okay. So maybe you think this defining the network architecture in Pytorch is very simple, okay? And the next thing is the Resnet architecture, okay? And here, Resnet appears in 2015, and I said it surpasses the human accuracy in image classification task, okay? This is the Resnet and made by some researcher in Microsoft, okay? But he left Microsoft after this, right? And he's now in Meta, maybe. And the motivation for making this Resnet is when stacking more layers. So you remember that in VGG, there was maximum 19 layers, okay? But people thought stacking more layers than these 19 layers may have to make the model better than the VGG architecture. Okay, but it was not the thing happened in reality. Okay, so I mean, this is the training iterations. This is the training iterations, and when you stack more layers than 20, let's say this is the model's training error having 56 layers. Okay. This is also the testing error of the model having 56 layers. Okay. Let's say this is the testing error and this is the training error of the model having 20 layers. Because this is the error, less is better, right? So you can observe that if you have more layers than 20, you may expect the performance have to be better, but in the reality, actually it gradually less than the original model. Okay, but when you stack 5 layers, for example, maybe this is the training error of the model having only 5 layers. So if you stack more layers, the training error and also the testing error may decrease, okay, until 20 layers. And then if you stack more layers, then the training and testing error both become high again, okay? So this is a strange phenomenon, right? And people investigated why this happened. And I mean, this happens because of the vanishing gradient phenomenon, okay? So I will first want to explain this vanishing gradient phenomenon. So basically, you have to get this gradient, okay? This is differentiation of loss respect to the image, right? The initial input, okay? So we have to define this kind of gradient when during the training, right? If the network gets deeper and deeper, let's say this is 20 layered architecture. This might be the loss, and this would be the initial input, okay? How this gradient work, maybe let's think about how this gradient is calculated. It would be calculated like this. So intermediate, let's say this intermediate output is Y1. So, and let's say this intermediate is Y2. So, and the next intermediate output is Y3, right? We have to multiply more than 20 layers gradient sequentially to get this gradient, okay? But if we have more and more layers, for example, in the network whose layer is, number of layers is 56, it had to calculate this, it had to calculate this, right? But in most cases, this gradient is less than 1, right? it is in the small scale, right? And if you multiply several floating values, which is less than 1, then this will converge to 0 because of the precision problem, right? So even though it has some value, this simplifies to 0. And because of this, the training is not happening properly, okay? So because of that, this Resnet comes out, okay? To solve this problem, this is called as the vanishing gradient problem, okay? The gradient vanishes to 0, right? So this is the this is the conventional architecture, right? So this is the input, and we apply some convolution operation and apply some activation layer, and then we apply convolution and so to output some output, okay? So previously, h of x is the the output we can obtain from the conventional convolution operation, right? But this time, we have one more path, okay? This is the residual block, which is the basic block of the Resnet, okay? We simply connect their initial input to the final output and then add them to the output, okay? So now the output of this residual block is this, okay? Additionally to the original convolutional output, we add the original signal to it, okay? If we do this, the gradient becomes like this, right? We have +1 term in our gradient, okay? Then this gradient, which was less than 1, becomes in the scale similar to 1, right? Every gradient is now having some value which is slightly larger or slightly less than 1, okay? Most of the gradient becomes like that, right? Then this gradient is not vanishes to 0 now, okay? It has almost, it has values almost similar to 1, okay? So how much layers we have, the scale of this gradient becomes stable, okay? So we can calculate the parameter update more stably than before, okay? So this Resnet, so this is the Vision&Learning architecture, okay? And this is the plain convolution architecture having 34 layers within it, okay? We can just add more convolution layers in this Vision&Learning architectures like this, okay? To increase their depth, right? And this is the Resnet architecture, which have 34 layers with this residual connection, okay? Because of this residual connection, the gradient anymore vanishes to 0 now, okay? So people could stack more layers to do this Vision&Learning. So, and they observed that still using this residual connection, if they stack more layers, the accuracy becomes better and better, okay? So the reason why, if we stack more layers, the performance reduces again was because of this vanishing gradient, and using this residual connection, we could solve it. And then we could make the architecture deeper again, and that result in the increased accuracy, okay? And this is the Resnet architecture defined in the Pytorch, okay? Okay, we have to define some convolution layers. So this is for convolution layers, and this is the same convolution with stride 2, okay? Anyway, we have to define some of the convolution layers with some stride here, okay? And then this bottleneck is the basic block for the Resnet architecture, okay? What they do in bottleneck is they have the main path. This is kind of fx operation, which is constituted with several convolutional blocks and apply some downsampling afterwards, okay? And when the input x comes in, what they do is they first calculate the original path output, and then they add the original signals here. So this is the implementation for this part, okay? This part, okay? So, and also if you do not involve some downsampling, you may use this code, okay? So X, you will add the original signal X without any downsampling, okay? And this is the bottleneck architecture with stride, okay? So this, they have to separate the original bottleneck into 3 because of some to fit the dimensions of the signals. But I mean, this is kind of the basic operation without considering any downsampling or the stride, okay? So we can just add the original signal to the output H of X, output Fx, okay? This is the original output from the convolution layer, and we have to add the original signal X to it, okay? Okay. And they stack multiple bottleneck layers, except for the first layer, having just convolutional layer, ReLU, and max spring. Every other layers are composed of these bottleneck layers, okay? And after that, they average through the final output and apply this FC layer to transform the final feature to the class probability vector, okay? This is the forward function, okay? So this is the Resnet, okay? So are you guys following this? Okay. Anyway, this is the CNN architecture implemented in the Pytorch, okay? And today we will continue to object detection pipeline. So we will, from now, we will learn about the object detection, Okay. So as I already told you, this object detection, not similarly to the image classification task. The image is having more than one main object. Okay. So we have to localize the object with bounding box representation, right? And have to classify that bounding boxes, okay, according to the object category, okay. So this is the example from the faster Rscnn architecture, one of the famous object detection pipeline, okay. And also for more fine-grained understanding of the scene, this kind of pixel-wise recognition is also performed, and their name is semantic segmentation. Okay. So for a while, I think we are focusing on this object detection pipeline, how to extend previous image classification network towards this object detection pipeline. Okay. And also we will also deal with the semantic segmentation task and their architectures as well, okay, afterwards. Okay. So the simplest way to extend the image classification CNN architectures towards the object detection pipeline is using this sliding window approach. Okay. So what they do is very simple. So for achieving the object detection task from the one image, we apply multiple bounding boxes by shifting one pixel at every time. Okay, we apply this kind of sliding window scheme to make some cropped images, and then apply CNN architectures to this cropped region. We can do object detection. Okay, indeed, when using the shallow learning algorithms, we did this to achieve the object detection. Okay. And also, because the objects are differently shaped, right? For some objects, this kind of squared boxes are suitable, right? But for some other objects, for example, for human, they are standing like this. So this kind of rectangle is better to capture human, right? To tightly capture the humans, this bounding box is better than the square, right? And for other objects, this type of bounding boxes might be better, right? So we apply several multi-scale windows in the images using this slide window method, okay? And that can achieve object detection task. And this is the simplest way to extend image classification network to the object detection task, okay? But this is inefficient, okay? Let's say there are 4 types of windows, and let's say this image size is 640 by 480, then we need this number of CNN operations, right? So this is huge, actually, and it may take 12 hours to achieve the object detection from the one image, right? And this might be bad, right? So instead of doing this, we may have to, it would be better to detect object by our hand, right? Okay. So this is not that good. So computer vision researchers are thinking of a better method to achieve the object detection from the CNN network. Okay. But indeed, in 2001, one famous facial detection algorithm, whose name is Viola-Jones face detector, it indeed do this type of sliding window method. Okay, it indeed performed this sliding window method. Okay, it first extract the hard-like feature, which is the hand-engineered feature. Okay. From it extract hard-like feature from this squared region. Okay, but they use only one type of bounding box because of most of the face they are in this they are fit to this square bounding box. Okay, and then they apply this hard-like feature extractor using this sliding window method, and then they classify it to binary. They perform binary classification with label for face versus non-face. Okay. They extract hard-like features for all the bounding boxes and classify if that region is face or not. Okay. And they actually use a boosting algorithm for this classifier, which is the shallow network. Okay. So even though they apply this number of operations, right? Let's say this image size is this. They achieve this face detection in few seconds, okay? Because their classifier is shallow and it does not take much time, okay? But in CNN, we cannot do that, right? Because CNN is composed of deep layers and it took a lot of time, right, for one pass, okay? So we had to think of different methods, okay? And one simple solution that appeared after this was the regional CNN architecture. This is called as Rscnn architecture. Okay. In this algorithm, they firstly generate this number of regions that may contain the objects within it. Okay. For example, from this image, it first generates this type of 1,000 bounding boxes, and their algorithm is actually called a selective search. Okay, and this selective search is not based on the CNN. They are not learnable, and they was independently developed before the deep learning algorithms. Okay, previously it already proposed. Okay, it independently developed. Okay, but these deep learning researchers are proposed to use this selective search as the kind of pre-processing module for object detection task. Okay, and it takes only a few seconds in using the CPU. Okay, they are basically the clustering algorithm. Okay. And they apply several clustering in the first part of the algorithm, and then they have some shallow running part as well. Okay, and actually there are multiple algorithms that can filter out this number of regions. Okay, but this selective search is one example out of them. Okay, and what they do is very simple as well. So their assumption is if pixels are belonging to one same object, their color, texture, size, shape might be similar. This is one assumption what selective search is using. Okay. So in an image, there are a variety of pixels, right? Let's say if image size is like this, then there are over how many? 30,000, 300,000 pixels within an image, right? And if two pixels are belonging to one same object, they might have similar color, textures, and size and shape, right? So, okay, using this prior knowledge, they apply some clustering algorithm on color and texture and other features, okay? Then they could obtain this type of segmentation map, okay? For example, these are obtained from the color features, okay? So if they cluster the pixel values within this image, these regions are having similar color, right? So the color encoding here is not that important, okay? But they are denoting that if they have similar color here, they are clustered as the one cluster because their features are similar, right? So pixels here are clustered as one. So it indicates that they are having similar color, right? And this is also similar, but we cannot decide we cannot decide the number of clusters, right? That is not optimally, it is hard to decide it optimally, the number of clusters, okay? So for one image, we obtain this clustering result multiple times using slightly different hyperparameters, which is the clustering, which is the number of clusters, okay? So for example, this uses 100 clusters, then this will use more than 100 clusters, for example, 500, okay? So for example, here, the region originally had just one cluster, but now it has multiple clusters in the same region, right? Previously, if they are in the blue scale, they were clustered as one cluster, but now still in the blue color, they have some dissimilarity. So they divide the regions into two, okay? Anyway, we cannot decide it optimally for different images, so they use several hierarchical hyperparameters, okay? And then they apply, they do this for color, texture, and other features, and they, at the end, apply some shallow classifier that can finally detect the bounding box, okay? So, yeah, at the end, they may have bounding boxes for these segmented regions like this, okay? And at the end, they also filter out those regions using some shallow classifier, okay? Anyway, this is one example of filtering out this number of regions that may have object in. So what they are assuming that is if they could have one bounding box which can tightly have objects, okay, these bounding boxes could be filtered out by the deep learning algorithm, which is the CNN, okay? So this number of bounding box, 1,000 or 2,000, that is less than this number, right? This is the number of whole pixels inside an image, okay? This is still large, but this is far less than this number, right? So their idea is rather than applying this number of operations for CNN, they could apply CNN for only these regions, okay? That is actually more than 100 times efficient, okay? So that is the idea of Rscnn, okay? This is the grouping algorithm used for the selective search, okay? They basically calculate similarity for regions and they merge, okay, until reach some threshold, okay? And this is the selective search algorithm already implemented in the OpenCV library. So I denoted here for, for show you that this OpenCV is having much features, okay? Actually, it calculates the selective search algorithm using these few lines of code, and this is for visualizing the bounding boxes, okay? And you can see the bounding boxes are capturing the object, okay, rather than the background, okay? And this Rscnn algorithm is using these 1,000 to 2,000 bounding boxes extracted from the selective search algorithm. And then they apply CNNs to these regions, to these cropped regions. So using this selective search algorithm, they crop the images, okay, and resize it. And then they apply pre-trained ImageNet pre-trained convolutional neural network to that regions. And then they regard the last layer's output as the feature. And then they train another SVM algorithm, which is the shallow learning algorithm, to classify its category, okay? So rather than using the hand-engineered feature, they extract the region-wise CNN features and then train the shallow learning algorithm, the SVM, to classify its class, okay? But there is some problem here. This was the original Rscnn algorithm, which is the regional CNN algorithm. But their limitation is here. So they are not end-to-end trainable, okay? So they have to apply selective search algorithm first, and then they have to crop it, okay? And then after that, this part is all composed of all trainable component layers. But before this cropping, it is not trainable, okay? But this is not ideal because, from the whole image, this specific part is separated, and then we have to detect their class, seeing only these regions, right? This is sometimes not easy to achieve. We sometimes have to use some context in the overall images, right? So, sometimes it is easy to understand the class of this region, seeing other part of the images. But in this Rscnn algorithm, only information lying on this region, specific region is used for classify their category, right? So this is one limitation in Rscnn. And another limitation is they are still slow. Okay, we have to apply this number of CNN operations to classify one image. Okay, that is the limitation. So maybe from our next class, we will learn about the fast Rscnn and the faster Rscnn algorithm, which result in better performance. Actually, this is accuracy. So when applying this faster and faster Rscnn algorithms, it shows better performance as well as time is getting faster and faster. Okay, so we will learn about this Rscnn more faster Rscnn algorithms in the next class. And also after that, we will learn about some transformer-based object detection pipelines. Okay. So we will do that in the next class. Okay, thanks a lot. I will finish today's class here. Okay.